Hi guys, I'm P.D. from IIT Madras. I'm currently a Grandmaster on Codeforces and I would be training the editorial for the problems A to E in today's Codeforces educational round 135. I'll try to give a quick editorial sort of for all the problems. Uh, I would encourage you guys to try to solve the problems after seeing the editorial for the problems you are unable to solve. And probably the quick editorial would help you enough to solve it up after that. You might still have some queries, try to work them out yourself. If you're still unable to get, feel free to put them up in the comments. We'll try to answer them. We start with problem A, uh, colored ball revisited. So you're given that there are n different color balls, and you're given the frequency of each color. And you're given that in one operation you can take two balls of different color and remove them. You're given that the number of balls are odd. You have to tell uh, the color which would remain at the end. If you just keep on doing, you have to output one color which can possibly remain at the end. And I guess one intuitive answer that you can give immediately would be that probably the color which has the highest frequency should possibly remain at the end. And it turns out that it is possible to do that. I guess in contest, you just go on doing like implementing it. We can sort of think about the proof in this way that suppose you sort all the balls in the order of their frequency. Where you have um, 1, 3, 5, 7. And now what you can do is take the balls in the first two first two colors and keep on taking them until the smaller one gets out. Then do the same for the next two. Again, that's until this gets out and keep on doing that. And at the end, the last one would remain. That's sort of like a for it. But I guess in the contest, it's not required. So yeah, that's problem B. I guess I will show my code. It's probably easy. I'll still show my code. So this is the code for each query. What you do is you take in the input. I have used this thing called array into. This is sort of like a pair if you know, and you can sort it based on that. And yeah, then you print the color of the ball which has the maximum frequency. The color which has the maximum frequency. That's problem A, colored ball is revisited. Now we will go on to problem B, which is best permutation. You are given the definition of a permutation, and you're given a way in which you can find the some value of a permutation. We define the value of a permutation this way, and it's defined as you start with x equal to 0, and then if the first element is greater than x, you add it to the x. Then you look at the second element. If it's greater than x, you add it. Otherwise, what you do is you assign x 0. So x changes to 0, and you have to find the maximum value. You have to find the permutation on length n such that this value is maximum. And I guess one thing which you can see is as soon as x gets greater than n at any point, then if you again do an operation, it would have to become 0 because any element in this permutation is less than equal to n. So if x becomes greater than equal to n at a point, then the next value it would become 0, which means that you can keep on incrementing x, and as soon as it becomes greater than n, that would sort of be your final value because you know after it would become 0, and you can think that before it becomes greater than n, it would be something less than n, and the maximum it can be less than n is n minus 1. So I guess I'll just show. So suppose you have 1, 2, 5. You add 1 to x, like x starts with 0. You add 1, it becomes 1. Then you add 2, it becomes 3. Then it becomes 8, and so on. At some point, if you cross this, it would become greater than n. So till here, it should have been less than n, and the maximum it can be less than n is n minus 1. And now you know that after this operation, it becomes greater than n, and you possibly want to end your array over here. Because if you do one more, if there is one more element over here, then you have to become 0 again. There could have been possibly elements over here. You don't care. We are looking at the last time x became 0 and then we incremented and so on. So at this place, it will become greater than n. And now this value also, you would want to be like, you want to maximize it. And this would be m, like the maximum you can, an element can be is m. So you can see that the maximum value your x can take for any permutation is 2n minus 1, which is 1 before it becomes greater than n, and 1 is the value it takes. So their sum can maximum be 2n minus 1, which you can see. And now the thing is how you make up a permutation which has this sum greater than 1. I guess I'll just show you my code for the same. I have done sort of like a bit of case work. There might be easier approach. What I'm looking at is, I know that just using the two elements, which is n minus 1 and n, I can need my x to be 2n minus 1. I just need these two. What I want to ensure is when my x comes over here, it's 0. So there should be some small element over here in such a way that when my x crosses over here, it becomes 0. Because if it's not 0, if it's say 1 or 2, then we will add this, it becomes greater than n, and then you add this and it becomes 0. So you don't want that. You want x to change to 0 over here, which means the value it came over for this element was greater than this element. So I'll just show you the case that I have done. One thing is, suppose if n is even, consider the case when n is even. Let's say n is 6. We know that at the end we want to place 5 and 6. And before that, what I'm doing is I'll just place this thing 4, 3, 2, 1. There's something you can just try to come up, like try to figure out cases yourself. There could be other ways as well. Like there's one way which it does. You start with 0, x becomes 4. If 3 is less than 4, it becomes 0. Becomes 2, becomes 0. So the idea is that every alternate element it becomes 0. And so at this point, it would be 0. This is one way. Similarly, for n, if n is even, you place n minus 1 and n at the end and sort of reverse the array before that, which ensures that the answer would come out to be 2n minus 1. And similarly, there's another case when n is odd. What you do is you place 1 at the start and reverse the remaining array. You will see that this also sort of works and gives you the element. This is just one possible solution. There can be multiple. You can try to figure out cases yourself and see how you can get 2n minus 1 at the end. The main thing is that the answer of a permutation can be at max 2n minus 1, and you have to sort of construct it. You can try to figure out some method by yourself as well. This was the method I used. That's problem B, which is best permutation. We'll go on to the next problem, which is C, digital logarithm. So in this problem, we are given two arrays, A and B. You are given an operation which you can do, which would incur you a cost of say 1 coin. And in that operation, you can take any element from array A or array B. You can take any of the element from array A or B, and you can change it to a number of digits in its decimal representation. This is also called as digital logarithm over here. So one of the key things to note in the problem is that each value is between 1 and 10 power 9. This is like one of the key observations that if you do one operation on any of these values, it would change to a number between 1 and 9. You can between 1 and 10 without including 10. So the maximum number of digits in the value can be 9. The maximum number of digits in the element can be 9. In one operation, it will become 1 and 9. And now in second operation, it will become 1. So you can see that on any particular element, you would do at max 2 operations. This is like one of the key observations. After that, we sort of follow like a greedy approach. I'll exactly jump onto my tool. The main idea is that you would do at most two operations on any given element. Now what we do is, this is a function which would count the number of digits in decimal representation. Now given n, we sort of take the input first. So I'm taking the input in multi-set because I want to remove the elements as well. There could be possibly other ways to do the same. So for the first array, I guess I will just yeah. So I take the input in a multi-set for the array A. Now, while taking the input for array B, I'll see if that particular element is already present in array A. If it is present, then I know that I can just cancel these off. Okay, I guess I missed that up. So our aim is to make array A and array B exactly the same by using some finite number of operations. We can see that it's always possible to do that because if you do this operation twice on all the elements, then every element will become one. It's definitely possible to do. You have to find the minimum number of operations to do the same. Again, DDD, we can see that if A and B have two elements which are same already, then you possibly just want to remove them and not do anything with them. So that's what I'm doing. If there's an element which is already in A, then uh, you erase it from A and don't push it in, like, don't insert it in B. While if that element is not in A, then you'd have to insert it in B. That's just sort of what's the sort of doing is that if the element is present in both the arrays, then you just remove it directly. Now, what we do is for each element in A, we know that uh, we know that if it is greater than 10, then at least once we would have to do an operation on it because there's no way we can change an element in B to a number greater than 10 greater than 10. So for every element in A which is greater than 10, you just change it to like you just apply the operation once on it. And now you know that all the elements in your array A would be between 0 and 9, between 1 and 9. So you apply the operation on the elements which are greater than 9. This is what I have done. This is the function count digits, which counts the number of digits in decimal representation. And because you would have to do the operation once, you increment your answer by 1. You would have to do this by at least once over here. And you also store the DP. The DP is basically just count of number of elements in A. Just like frequency of each element in A. Now for each element in B, again, if it's greater than 9, you know you have to convert it to get like you have to apply the option at least once on it. This is what we have done over here. And now, if the number we converted to is present in A, then we just take both of them off. You don't have to do any addition moves. While if that particular element is not in A, then you know that at the end you'll have to change this particular element to 1 and some other element in A which would remain to 1 as well. So the only way you would be able to cancel the element off is you change this to 1 and a particular element a particular element in array A to 1 as well. So you have to do that twice. So you add 2 and you can just see that if this particular element is 1, then you won't do this operation. So you can increment 1 over there. And also, if there are some elements left in A which are 1, then you won't do the operation on them as well. So you subtract that as well, and that's your answer. I guess that's the solution for C. If you still have any queries, you can look at the problem, look at the code later on, and you can try to think about it yourself as well. So that's the editorial for C, digital logarithm. Now we'll go to D, which is letter picking. So D is, I guess, a bit standard question, I would say. You would have probably seen some sort of question like this if you had done some problems on DP. Nevertheless, we will go on to the problem. So we are given that there are two players, Alice and Bob, playing a game. They are given a string S consisting of lowercase leading letters, and they sort of have their own strings, which is empty to start with. Each turn, they would both take up one character from the string S, either from the start or from the end. And the player which gets the lexicographicaly smallest string at the end, uh, that player wins the game. And you have to figure out if both of them play optimally, then who would win the game. This is a standard DP problem. I guess you can see that the constraints are till 2000. So you can see that it would be an insecure solution. And in generally these sort of problems, you can see that it would probably be a DP solution, but you would have a DPIG stream. That's sort of like the intuition to think that's why it would be DP. And I guess if you had done some problem on DP, you would know that in these sort of problems, like what is typically how we define DPIG. So, anyways, I'll start with the logic. So, yeah. So, we'll use DP to solve this problem, as I said. We will define a state DPIJ, where DPIJ would tell you if we just take the substring I to j, then who would win? So that's how you would want to define DPIJ. And now you can see that your DPIJ would result in DP of 1 comma n would result in who would like is what is demanded. So note that n is even. So n is even. So we know that both of them would have a string of equal length at the end, and ls starts to move. So we define DPIG as the player who wins starting first, and we always construct this DPIG for even length of substring. You will see why that's sort of required. Yeah, we'll go on to the code and sort of explain it with that. So this is the code for the problem. This is just taking the input. I have defined DPIG to be 1 when the person who is going to play right now, who takes the first move, which would be ls, wins 0 if it's a draw, and -1 if ls loses. So you can consider it equivalent to be like for the first person, or say ls. 1 if ls wins, 0 if it's a draw, and -1 if ls would lose for sure. We initialize everything with 0. And now for 2 consecutive characters, you can see that if there were just 2 characters, if both of them are same, then no matter whatever ls take, Bob will take the other, and it would be a draw. While if one of them is smaller, like if they are different characters, then ls can take the smaller one of that, and the Bob would have to take the bigger one, and ls would win. So for this is out of the base case. For length 2 substrings, we can define it this way. Now we will code for length greater than 2. And again, we're coding up only for the even length substrings. You'll sort of see why we are looking into that. So like basically, if we say take or substring, we need to know what was the one character which the other person took away. This is sort of a bit confusing. So we'll work on with even lengths. And yeah, so we go on to all the substrings of length 4, then 6, then 8. And what we do is we define these 4 characters, which are like AI plus 1, AJ minus 1, and AG. This is our substring. So we know that it's of even length. And these are the 4 characters, WX, YZ. Why these particular characters? Because we know that in our first turn, Alice can take either W or Z, and after that, if she takes W, Bob can take either X or Z, and if she takes Z, Bob can take either W or Y. So these are the 4 characters which would get affected in 2 moves at the worst. So these are the 4 characters which can get affected in the next 2 moves, which is like one Alice's move and one Bob's move. Now let's see the code. So if Alice takes W, this is for the case when Alice takes W. Now Bob is left with this string, which is X dot 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 YZ. So in this case, again we know that Bob plays optimally. So Bob will first try to see if there is a way in which he can win. Then if there is no such way, he will try to see if there is a way in which he can make it draw. And if there is no such way, then he knows that he would have to lose. And yeah, and similarly, like so, when Bob has a winning way, then we know that that particular move for Alice would make her lose. So let's see what we do. So yeah, this is when Alice takes W. Bob has this string. So what Bob can do is Bob would ask, if I take dp I plus 2 to j, so in this thing, if in this thing Alice loses, which means that no matter how Alice plays, Bob would have a string which is lexicographically smaller, then these two characters, which is like W appended at the last two in Alice string and X appended at the last two Bob string, won't make a difference. I guess maybe a diagram might be better in this. So suppose we have two strings S1 and S2, and S2 is less than S2, S1 is less than S2 lexicographically, then no matter what character W and X you append, it would still be less. This is just followed from the definition of lexicographical. You can sort of try to see it up by writing it down if it's not clear to you. But yeah, if S1 is less than S2, then no matter what you append, it would still be, this combined string would still be less than this combined string. That's sort of the main idea. So if dp I plus 2 to j, which is the string, if in this particular substring Alice loses, that is, this is -1, that you know that Bob will just take X if Alex takes W, and now Bob would get a smaller string in this, and hence he would win. So in this case, Alice would lose. Bob would win. Bob has a way to win if Alice takes W, and thus Alice would lose. They have defined three counts, which is like count is the number of cases in which count W is number of cases in which Alice wins, number of cases in which Alice gets a draw, and number of cases in which Alice would lose. So in this particular, so like there are two cases: Alice takes W and Alice takes Z. Yeah, so she takes W, and this is -1, just like dp of this is -1. Then you know that Bob can win, and so Alice would lose. This is count of L plus plus. Similarly, if this dp is -1, then again Bob would win and Alice would lose. Else, if X is less than W, lexicographically, X is less than W, and dp of this is 0, which means it's a draw. So if it's a draw, then both of them have the same string, and now at the end, Bob is able to put a smaller character, so Bob will win. So if dp of this is 0, this string, which means it's a draw for that particular substring, but Bob can take the smaller character, then again Bob wins. So Alice loses and count of L plus plus. And similarly, you have this case when again Bob can win. And similarly, there are two another cases when Bob can make a draw, when this is draw and this was it. So again, note that we are going in priorities of Bob. If if he is able to make a win, he would first want to do that. But if he is not able to win, then I would try to see if I can at least make a draw. And if he is not able to do that as well, then you know he would have to lose no matter what he does. So that would be a win for him in that particular case. And you simply do it for the other case, and you sort of see what are the outcomes of both the cases. So if in at least one of the moves Alice can win, then she would take up that move and dpij would be won. Even if she can't do that, but in at least one of them she can make a draw, then she would want to do that, and so dpij is 0. But if she's not able to do anything, then probably she will lose and dpij is fine. In general, the code should be self-sufficient for understanding. They can still go through the code again and let me know if you are still able to have any confusion. I guess the main thing is defining the DP states and how you would make up the transition. Again, for transition, the important thing is sort of see what are the cases for Alice, and in each case, what is the best thing for Bob, what is the next best thing for Bob, and next best thing. That's sort of the core idea. So that was the solution to problem D, letter picking. Now we'll go on to the last problem, which is red, black, pepper. Yeah. So the problem is pretty like written pretty simply. So monocarp has n dishes, and he has two powders which you can pour on each of the dish, which is red pepper and black pepper. And there is a tasteness of a dish, which is AI if you put red pepper and BI if you put the black pepper. And he can go to shops which gives uh, X red pepper and Y black pepper, and you can take any multiples of these. What you want to do is, uh, for a given shop, you want to know if there is some way, like you want to know if there is some way to take uh, x times xj. Xj is the number of red paper that shop sells in one packet, and yj is the number of uh, black pepper packets that shop sells. So like number of black peppers in one packet. Yeah. And so you want to see if somehow it's possible to make up exactly n peppers together and now put them into them in some order. And if it's not possible, you put print -1. But if it's possible, what you also want to know is what is the maximum tastiness of your n dish together, which you can get. Yeah, that's what you want to do. One thing you can see that the tastiness is upper bounded by sum of max of ai comma bi. Because like each dish can be max of ai comma bi tasty, and sum of it is the upper bound. So the maximum tastiness of your dish can be this thing, and if you sort of are not able to buy, and this would happen when for the dishes which you should give red pepper, you give red pepper, and for the dishes which you should give black pepper, you give black pepper. So that's the exact thing you would have to do to get the maximum tastiness. But in other cases, what might happen is that you sort of are unable to buy the exact number of red peppers, so you buy more red peppers than required. So for some dishes, you would be putting up red pepper when putting black pepper was optimal, or you could have be doing the converse way. So let's see how we would do this problem. Um, I should go to my so I'll directly jump to my code. So to start with, what we are doing is we find this best value, which is like the upper bound. So best, this is like the value A and value B. So here A defines red pepper and B defines black pepper, and these are their values uh, for each dish from 1 to n. Now your best is this just maximum of A comma B. And now if the tastiness you get is higher with red pepper, then you put it in the red array. While if it's higher for B, then you want to put black pepper on it and you store it in B array. Uh, what you actually store it is not their exact values, but you store the difference. This difference is how much you would lose in tastiness if you put black pepper instead of red pepper. So here we know putting red pepper is optimal, but if you're not able to do, then you would lose this much value. And similarly here, if you are unable to put, you would lose this much value. And you sort them and reverse them. So basically, if you know that you would have to put red pepper instead of black pepper for 5 dishes. Maybe I guess some a diagram would make it clear. So you know that you have 10 dishes which are optimal, like which give good like best tastiness with red pepper, and there are say 17 dishes which give the best taste with black pepper. But somehow, for some reason, you're not able to buy exactly 10 and 17. If you had done that, you would get the best tastiness, which we are calculating. But if you don't do that, suppose you can what probably do is you are able to buy 12 red and 15 black. In this case, what you would do is For these dishes, they wanted black and you're able to give black. For these dishes, they wanted red and you're able to give red. Why? For exactly two dishes over here, they would have given optimal result with black, but you are putting red on them now. And you know that these two can be selected, like these two can be any of the 17 dishes. And so you'd want to take those two dishes, which gives the lowest decrement. So like that would decrease the taste the least. And so that's why we store this different and we sort them based on this difference. And we also calculate the prefix sum of these. So we suppose you sort them based on their uh, decrease in tastiness. So you know that there is one dish which would give -1, one which would give -2, one which would give -5, one which would give -7. So if you have to just spoil one of these dishes, then you want it to be this. If you know you have to spoil two, then you would take these two, then these two, three, and these four. And if you take, say, these three, then your tastiness would decrease by their sum. So we store the prefix sum for that reason. And now for each query you want to solve. First we will, so there are multiple functions in this problem. So first you can see this basic function, which is like get taste. So suppose you have count A number of red pepper and count B number of black pepper. Now what will be your cost? This is for the case when you don't satisfy the condition at which you would get return -1. And otherwise, if you follow satisfy the condition, which is like the sum is n, then um, you define answer to be best, which is like the maximum most optimal it can be. And if count A is greater than PA, so PA is this value, the number of dishes which give optimal for red. And if your count A is greater than PA, which is exactly this case, then you know that for exactly these many dishes, count A minus PA, you would be spoiling the black dish, like the dish which requires black pepper. And so you would add to your answer the prefix sum of L values, which say in this case would be -1 plus -2, which is -3. So you would subtract, like add -3 to your best value, and that would be your answer. And similarly, if count A is not greater than BA, then probably count B would be, and in that case you do the same for the black pepper. So given some count, this would be your answer. And now it's the tricky part. For you're given a shop which gives peppers in this set. You can buy uh, any multiple of X number of red pepper and any multiple of Y number of black pepper. And yeah, so you can see that uh, this is the number of peppers we can buy, and this is should be equal to n. So you can see that GCD of X and Y would divide this and this. This should divide n as well. This is a sort of a standard thing. So you find the GCD of X and Y. If n does not divide G, their GCD, then it would be -1 directly. Because you know it can't, no combination of X and Y would like give you n. But if that's not the case, then we do something else. Let's look at this function for now. So what we do is we start with I equal to 0 and keep on doing it. I here denotes the number of packets of red pepper that you buy. It can either be 0 and it can go up to infinity. If you buy I packets, each packet has X red peppers. So you would have a total of I into X red pepper. This would be the number of black pepper, and this should not be greater than n. And this should also be divisible by y, the number of black pepper. Yeah. So that is that. If you're able to do that, then your answer is get taste of these values. And so you can simply maximize your answer with this. But if you would sort of write it down, you would see that if we do this for if you do this, then you would, yeah, you would possibly do, you can possibly do two money operations, right? When x is pretty small. So we sort of bound x. If x is bigger than a certain value, then only then you do this. And so you know that it would take n by x number of operations, and we can sort of optimize that. So you do this only when x is higher than some constant. Similarly, if y is higher than some constant, we can again do the simple brute force. But if x and y are both small, then you can do something else. What we do is we find the first value for which x satisfies this, and then we know that we can get remaining values in some way. So, suppose you can make n, suppose x was say 3 and y is 7, and probably let's take an example for n as well. Let's take n to be 100. Now you know that if you take 3x and 13y, then you will get 100. 7 times 13 plus 3 times 3. That would give you 100. So that is like the smallest value of x for which you can get it. But now you can see that you can do some trick. You know that uh, if add you add 7 times 3 over here, and you subtract it from here, then as well it will sum up to 100. So if you take their LCM and sort of add one on the other side, one on one side and subtract it on the other side, it will still sum up to 100. And so another possible solution is 3 is taken 3 plus 7 times, which is that 3 is taken 100 times, while 7 is taken 13 minus 3, which is 10 times. So you take 7 and 3 both 10 times, and you will still get 200. There's sort of like a fact which you would probably know if you're coming up to this problem. Yeah. So if the two values are satisfied, then adding their LCM on one side and subtracting from the other side would also satisfy it. Yeah. So in those cases, what you do is you first find the minimum value of x for which it satisfies, and now what you do is you find the LCM. This is the LCM, and yeah, and now what you do is you sort of keep on incrementing x. Suppose you saw that the x was still here. Now you keep on incrementing x with the LCM. This is the LCM until you know that it would cross this. So this is the number of dishes on which you're putting red pepper. Right? So if there are more dishes on which we can which want us to put red pepper on them, and we can as well, like we have edged to red peppers, so we'll keep on doing that. So for these dishes, we keep on adding red pepper until we know that if we do it more, then it will spoil black. So what happens is we find this particular number, and the answer could either be optimal for this particular value, or that you add it once again and you spoil some black, and that could be your answer. You know that if you do it again, then you will only going to spoil more black value. So you don't want to do that. Your answer will be either the value for this or for this. And it's exactly what you have done. So you can look at the code again if you want to know exactly how we calculate these values. But yeah, so this is how you calculate the two possible answers that could be there, and the maximum of them would be your answer. That's sort of like a quick solution for E. I guess E might still be a bit confusing. You can possibly look at the code again or read, try to think about it a bit yourself, but you'll possibly be able to get. I hope the code helps in that. So these are the solution for problems A to E. Yeah, that's it. If you still have any queries, I would recommend you to try out the problems now once you again yourself. Try to work on the things by taking out sample cases yourself and try to see if you're able to do better now. If you still have any queries, put them up in the comments. Thank you.